going to happen then. Okay. So we're on page 246 in the book, section 4.6, called Related Rates. Last one in the chapter. And just so you know, anyone viewing this, I'm wearing my pajamas because it's pajama day. I don't normally dress like this for school. Okay. All right. So the author does a pretty good job of explaining what related rates is, except for he does it just before the solution strategy. So I actually want to read you that one first. It's down there just before the blue box. I want to talk to you about what's going on. And then I'll come back and do some things in example 1 to show you what you're up against. Your first exposure to this method of doing things is going to freak you out a little bit. Just deal with the discomfort. It will become easier as we go along. You'll get used to it. Okay. Right down there where it says solution strategies, he says, what has always distinguished calculus from algebra is its ability to deal with variables that change over time. So not only do we not know what they are, they might be changing values as we move along. That's what calculus does. That's what the leap into doing mathematics when we discover how to use calculus. Example 1, which I haven't done for you yet, but example 1 illustrates how easy, and it is easy once you get used to the idea. Example 1 illustrates how easy it is to move from a formula relating static, meaning variables that don't move, to a formula that relates their rates of change. And it always is over time. As time moves along, how are things changing? And then he says, and I don't know if you want to call this simply yet, it says simply differentiate the formula implicitly with respect to t. This introduces an important category of problems called related rates, and still constitutes one of the most important applications of calculus. You will definitely see at least one, probably more like 2 different related rate problems on your final exam. They're that important, and it's that powerful, and it's really cool. Okay, so let's take a look at example 1, and I'll show you the notation of the things we write. Try to explain to you what's going on. If it doesn't make any sense, it will before we're done. Just deal with it. It's okay. So in example 1, it says, assume that the radius r of a sphere is differentiable function of t, d be the volume of the sphere. Find an equation that relates d dt and d r dt. What we're saying, folks, is we're imagining a sphere. It's like blowing up a balloon. And as you blow it up, the radius is changing. And if you blow it up at a steady rate, the radius is changing at a steady rate, right? As time moves along. So what we do is we differentiate implicitly, and in doing that, introduce the time variable, which is not in it normally. The velocity of a sphere, statically speaking, is 4/3 pi r cubed. If you know what r is, cubed I said. If you know what r is, you take it times 4/3 pi, got your volume. If you know the volume, you can find the radius by multiplying by 3/4, dividing by pi and cube rooting. But that's if r and v are static, not moving around. You blow up a balloon, everything's dynamic. The radius is changing, the volume is changing. Here's how we figure out how the rate at which the volume is changing is related to the rate at which the radius is changing. Both are changing. So we write dv dt. You go in dt, where did dt come from? Usually it's dv dr, right? This is the change in volume with respect to the change in time. That's what this means. So I'm introducing the time variable because we're blowing up a balloon, basically. And it equals, over here, it's going to be 4/3 pi. That's just the constant. Times 3r squared dr dt, chain rule. This is the rate at which the radius is changing as time changes. So it's implicit because we let r be the variable here, and I just stuck the constant out here because I don't want to talk about that right there. But the derivative of this would be 3r squared, right? Yeah. Times the derivative of the inside r with respect to t. That's the implicit part. And so when we clean it up, we get the 3's cancel, and we end up with 4 pi r squared dr dt. dv dt equals that in the simplification. And believe it or not, this is how the volumes change is related to the radiuses change. This is it. This is done. Okay, let's do the second one. The B part says, assume that the radius r and the height h. So now we got 2 variables. of a cone are differentiable functions of t, and let V be the volume of the cone. Now we are to find the equation that relates dV dt, dr dt, and dH dt. Just don't forget the chain rule and put an ET with it. You'll be okay. So the volume of a cone is 1/3. I'm going to put pi over 3 to keep the constants together. Is that okay?
Yep.
Pi thirds r squared h. And because there are 3 variables, and 2 of them, in whatever form they're in, squared or single, are being multiplied, we have to apply the product rule. So we say dV dt equals, I'm just going to leave this guy hanging out here. Now I got to apply the product rule. It's the first times the derivative of the second. Did you catch that? Plus the second times the derivative of the first. Chain rule with respect to t on each one. And then we do just a little bit of cleanup here. It's going to be pi thirds r squared dH dt plus 2rh or hr, wait a minute, 2 pi thirds. There's the 2 right there. 2 pi thirds. I'm losing my mind. R h dr dt. That's how dV dt, the rate at which the volume is changing with respect to time, is related to the rate at which the height is changing, is related to the rate at which the radius is changing. That mess right there is how they're all related. Okay? We are going to use that strategy of deriving implicitly with respect to t, as we do several story problems. 3 of them, as a matter of fact. We're just going to do 3 to demonstrate. And then you're going to, then you get to apply it. It'll be really fun. I do want to go over the strategy on this one so that you can see that I'm following it as I go along. I don't know if I'm going to do that. Maybe I'll come back to the strategy after I do the first one, show you my thinking, talk to you about what I'm doing. And we'll come back to the strategy so that if you need to refer to the strategy, you know what each one of the things means. Here's our first example. Well, story problem. A hot air balloon is rising straight up from a level field, and it is tracked by a rangefinder. You may not know what that is, but you will before we're done. It's being tracked by a rangefinder that is 500 feet from the liftoff point. At the moment that the rangefinder's elevation angle is pi fourths, the angle is increasing at a rate of 0.14 radians per minute. How fast is the balloon rising at that moment? You ask any common person this and they say that is impossible. There's too much there. I don't understand what's going on. There's just too much happening. This is a very easy problem. It is. Here's how you tackle a problem that's a related rate problem like this. You draw a picture. Every time you draw a picture of what's going on. Because more than likely, the equation that relates everything is geometrically oriented. So you need a picture. You can remember your geometry a little bit. Okay? So here's my picture. Here's my level field. If it wasn't a level field, then we'd be using law of cosines and sines, but we're not. Here's the balloon rising right straight up. Over here. Right straight up means we got a right angle there. I have to interpret that. By the way, you won't get pictures like you see on the left there, on the left of your example. You're not going to get pictures most of the time in your problems. You got to read the words and draw them yourself. Here's the balloon up here. That's pretty crappy, but oh well. And here's the rangefinder. And what the rangefinder does is it keeps the balloon in its scope. So it's sitting right here, and as the balloon starts to rise up, it rises up. It's on a little swivel here, and it rises up, keeps that balloon in sight all the time. Okay? So it's looking up here like that, and we need to fill in some details, but here is the key to solving these, right here. Never, never, never put a constant on your picture unless it's really a constant. If something's changing, if something is changing as time moves along, do not put a constant on your picture to represent it because that freezes it. He calls it freezing it in his strategy. And this balloon's moving up. The rangefinder is following it. All those things are moving. The one thing we know for sure that's not going to change over time is this distance right here. Liftoff point, rangefinder, 500 feet apart. That's not going to change. However, this is, so give it a name that you can remember what it means. This is changing. Give it a name that represents what you can remember. I mean, theta generally represents an angle, h for height of the balloon. Don't ever put anything right on your picture that is a constant if that particular variable is changing. Record it somewhere else. Like over here. We're going to freeze the picture at pi-fourths if you'll remember the reading of the problem. And at that moment, this, and this is how you interpret, the angle is changing at that moment, 0.14 radians per minute. Is it per minute or second?
Yes.
Minute? Yeah. So we're recording some facts over here. Don't ever put it right on your picture because it will cause you to write the wrong equation and you'll be deriving constants. And constants derivatives are zero, whereas variables derivatives need to be accounted for. So don't ever, ever put on your picture a constant number like pi-fourths if that's something that's changing. So let's read it again. So the hot air balloon rising straight up from the level field is tracked by a rangefinder 500 feet from the liftoff point. That is a constant. At the moment the rangefinder's elevation angle is pi-fourths. The angle is increasing at a rate of 0.14 radians per minute. We recorded that. The question is, how fast is the balloon rising at that moment? And you have to know what to call that. How fast is the balloon changing or rising at that moment is dh dt. That's the rate at which height is changing at this instant in time. That's what we're looking for. Okay? Then, once you've decided what you're looking for, what you've been given, constants, variables on a picture, now you have to look at your picture and decide how they are related with some geometry or trigonometry. What do you think? How are the things on that picture related? You maybe think Pythagorean theorem, but we don't want to know anything about this distance. We don't care about. Tangent would be excellent. Because with respect to that angle, we wish to know something about that, and we do know something about this. Tangent of theta is equal to h over 500. Does that make sense?
Yep.
Okay, so that's what we write. We look at the picture and try to figure out some mathematical relationship. Tangent of theta equals h over 500. Once you've come up with that, you derive with respect to t. Just get after it. Now, you could, if you wanted to do one thing before we start deriving, I like it better, and that is to cross multiply and flatten this thing out. I don't like dealing with fractions if I can avoid them, and it's a real easy avoidance on this one. Got it? So now we start deriving. What's the derivative of this side? What is it? Secant squared theta. Theta dt, yeah. Wow. Equals, what's the derivative of h? dh dt, which is a really happy thing because that's what I want. All I got to do is pi-fourths here and 0.14 here. And I will know how fast the balloon is rising at that moment when we freeze it at pi-fourths for an angle. So, it's 500. We can, if you want, you can evaluate it here if you like. I think the answer's in decimal form. We could also put it in radical form, though. He's got it in radical form all the way to the end, but if you want, you can just plunk it in there. That would be to do this. 1 divided by the cosine of pi-fourths squared. So you have double parentheses there, triple. And then times 0.14.
I got 140.
Is it exactly?
Yep.
Wow. I think that's because this turned out to be like a root 2 thing, and when you square it, you just get 2, so things come out nice and whole and wonderful. 140 what? Feet per minute, which is about right for a balloon. I mean, they don't rise up very fast, and they get a whole minute to rise 140 feet. Now, what?
Yep.
Question? All right. Now, before we leave it, let me show you the strategy that has so you can see how it applies to each piece. The strategy says, understand the problem. Figure out how high the balloon's rising at that instant of time. Okay, so that's what we did. We understood the problem, develop a mathematical model. That's this part right here. We're already to here. When it says understand the problem, it's in understood in there. Draw a picture. Write down what you have. Write down what you want. And then the second step, it says develop a mathematical model for the problem. And he says draw a picture. Many of these problems involve geometry. And label the parts that are important to the problem. Be sure, and he has this in italics, be sure to distinguish constant quantities from variables that change over time. Only constant quantities can be assigned numerical values at the start. Number 3, write an equation relating the variable and rate of change, right there, okay? Differentiate both sides with respect to t, that means implicit. Apply the chain rule for the implicit part. Number 5, and this is really, really important. Substitute values for the quantities that depend on time. And then here's a big thing. This is what's going to kill you. Write it out up front. If you make mistakes, this will be where it is. Notice that it is only safe to do the substitutions after you differentiate. You plug in pi fourths here and some h value here. I don't know what it would be. Maybe you could figure out what h is with trigonometry and plug in a constant here and here. As soon as you differentiate, they're both 0. Don't plug things in until you have got the derivative. Don't. Get the derivative first with the variables that are changing. It says, substituting too soon freezes the picture and makes changeable variables behave like constants with 0 derivatives. And then number 6, interpret the solution. Translate your math results into a problem setting with appropriate units and decide whether the results seem reasonable. That's what I did when I got the 140. I said, yeah, with balloons, that seems reasonable. It's got a whole 60 seconds to rise 140 feet. That seems like a reasonable thing to me for a balloon. If it were an arrow or a bullet, that wouldn't seem reasonable at all. So you make sure it seems reasonable. Okay, we're going to do example 3. Please don't turn the page. Just look at the presentation of the problem and let's see what we can come up with. And then we'll turn the page and see if the solution is correct. So don't look yet. What we've got is a cop trying to catch somebody who's running away from him, and they both have to, they have to turn a corner. One of them's traveling on a perpendicular street to the other, and the cop's got to get to that corner and then turn the corner and start chasing the guy. That's what's going on. So let me read the problem. He says, a police cruiser approaching a right-angled intersection from the north is chasing a speeding car that has turned the corner and is now moving straight east. When the cruiser is, now we're getting all our constants, so let's try and draw a picture. He's coming from the north. So here's the policeman coming in this direction, and here's the corner. So the streets probably go like this, but he's got to turn a corner, and the other guy's over here. So here's my car. Here's the guy running away. Here's the cop. I'm not going to draw him. I'm just going to put, here's the cop. Well, I'm not going to put him static. Cop's on this line. Here's the guy trying to get away, and he's approaching a right angle corner. So the cop is moving in this direction. The car is moving in that direction. You okay with that?
Yep.
Okay, so that's how I interpret the words. And that's what you have to do with drawing on picture. Then it says, when the cruiser is 0.6 miles north of the intersection and the car is 0.8 miles to the east, so I put 0.6 here and 0.8 here. Is that right? No! No. Are these things changing? These things you put the numbers on? Then don't put them on the picture. Don't sucker for that. What do you want to call this thing right here, this distance? I want to call it Y.
Yeah, that's Y.
I'm going to call this one
That's
X.
Yeah.
And I'm putting them on there as variables because they're changing.
Yeah.
So, what is Y when we do want to freeze it? 0.6. What is X? 0.8. Keep track of that over here. Put the variables on here. Don't put those on the picture. Okay? And it says the police determined the radar that the distance between him and the car is increasing at 20 miles per hour. Oh, here's some more information. If the cruiser is moving at 60 miles an hour at the instant of measurement, what's the speed of the car? What did they just give us with the 60?
So the speed of the cruiser is at
They gave us dy/dt, didn't they? And what is it?
60.
It is not. Here's another thing you got to watch out for. What is it really? It is negative 60. Why is that?
It's going down the
Because
y-axis.
y, the length of y is diminishing. The rate of change is making it smaller, and this is a rate of change. The rate at which y is changing with respect to time is negative 60 miles an hour because it's getting smaller. Be very careful with that. If the thing that you're looking at, if your variable is changing over time and it's getting smaller, your rate of change has to be negative. Watch it. Be very careful. So what did they tell us the XDT is? Because that seems to be something we want.
It's increasing by 20.
No. What is the XDT? It's what we're trying to find. Yeah. Look at the very, very last part of the statement. If the cop car is traveling at this rate, how fast is the escape car going? That's the XDT. How fast is he changing? Do we expect that to be positive or negative? Positive. He's trying to get away. His is getting longer. Okay. Now, the cop will say that the cop, just to finish drawing the picture, the cop is measuring the distance between him and that as he's moving along. As he's going this way, and this guy's going this way, he's got a radar gun and he's measuring the distance between them.
That's exactly what I was thinking. He's gonna blow that point.
Oh, he's got a partner. His partner's gonna.
Oh,
He's driving. Okay. So if he is clocking this distance, we need a name for it. What would you like to call it?
Q. I like
Two. No, not two.
Q.
Oh, Q. All right, we'll call it Q. Okay, you call that distance Q. What do we know about Q? Anything?
Increasing it by 20 miles per hour.
We call that dq/dt. At a certain instant in time is changing. Is it getting bigger or smaller?
Bigger.
Bigger. So this is 20 miles per hour. That's how fast that length between the cop car and the other car is changing at a certain point in time. But that is also a variable quantity, so it just has to sit there as a variable. What do we got to do? Look through the words and see if there's any more information. They told us at a certain instant in time when we do decide to freeze the picture after differentiating, this guy is 0.6 miles from the intersection. This guy is 0.8 miles from the intersection at that instant. And the cop car is traveling at 60 miles an hour, but his distance is diminishing, so it's negative. We wish to know how fast I don't know if he's a criminal, but the guy he's trying to catch, we don't know how fast he's going. And he told us that at this instant, when all of this, 0.6, 0.8, and that the rate at which it's changing is 20. The rate that distance is changing. Anything else that was in the work? We haven't recorded yet? Okay, so now that we've got things recorded and listed and kept track of, now we got to figure out how these guys are related to each other. It's not hard. Pythagorean theorem. So y squared plus x squared equals q squared. And they are all variables, so we don't plug anything in yet. We differentiate with respect to t. So what would this one be?
Good.
Okay, can you see that I can knock a 2 out of everything?
Yeah.
I don't want to deal with the 2's. That happens with Pythagorean theorem. If you're doing that, the 2's can just be knocked out there. Okay, so I've got everything. What is it that I want to find? The XDT? So before I do any plugging in, I'm going to isolate that. You guys are good algebra students. I'm going to isolate the dxdt first. So x dxdt is equal to q dq dt minus y dy dt. And to save myself a line, I'm going to divide this by x. Okay, so now that we've got the derivative done and we've isolated we've done all we can do with it. Now we start plugging things in. Dx dt is equal to, what's q? Oh, crap, we didn't find q. We will in a minute. What's dq dt? 20. What's y? 0.6. What's dy dt? Negative 60. What's x? 0.8. What's q? Now it's okay to freeze it and actually use the Pythagorean theorem to find q. It's going to be 1. Right? Because you have an 8 and a 6, you'll have a 10 here. That's Pythagorean theorem. But it's points things, and so it's just 1. You agree?
Yeah.
Okay, so sometimes you got to go back and find things that you didn't find before that you find you need. Q by Pythagorean theorem on this instant of time is 1. Okay, so now do the arithmetic. It's going to be 20 plus 36. 56 divided by 0.8, 70. So at that instant, now that doesn't mean that the cop car, when he comes to the intersection, if he's going 60, he is not going to make that corner going 60. What we're saying is, and in this snapshot in time, he is going 60. This is changing at 20. This guy at that instant is going 70. He may be speeding up or slowing down depending on the situation, but that instant, he's going 70. Can you see how if we forgot this negative, that would have changed things? Because we'd have had 20 minus 36, which would have made no sense. Would have meant he was coming back this way, which is not. So if your variable is diminishing, then its rate of change must be negative. Okay, turn the page, see if we're right. Okay, 30 miles an hour. Ready to go on? This next one is particularly difficult, so hang in there with me and wake up if you're sleeping. There will be one like this next one on your test, but it will be even more difficult than this one. And I will go over it with you, and hopefully with the explanation, you'll understand well enough to do it. It's worth a lot of points because it's a hard problem. I'll tell you up front, it's hard. Here's our situation. And I know that picture's staring you in the face. Don't look at it. Don't look at the details of it. Let's even draw our own, because most of the time all you get is words. It says, water runs into a conical tank. So root word of conical. Cone-shaped tank. At a rate of 9 cubic feet per minute.
It's actually quite convenient.
What?
Oh, I was just saying, what's the point of having a cone?
Oh, my uncle, he's in construction. He's always asking me how much gravel should I order for this cone-shaped septic tank, or cone-shaped whatever, fuel tank or whatever. They put the spigot at the bottom. He can never remember the formula or how to use it confidently. So, the moral of that story is, if you don't know how to do math, as long as you know someone who does, you'll do it. Okay, so here's what's going on. Water runs into a conical tank at a rate of 9 cubic feet per minute. The tank stands point down and has a height of 10 feet and a radius of 5 feet. Are those things static?
Yes.
Yes. Two things are.
Is the 9 feet per minute, is 9 cubic feet per minute, is that a static thing?
No.
Okay, but we can put the 10 and the 5 on the tank. That's not going to change as we fill it, right?
Yeah.
Okay.
Why is that not like steady?
Yeah, why is it not a constant?
Per second?
Because, well, it's a steady fill rate, but things are changing as we fill it.
Because you're going to get the same 9 feet.
It's not going to be the same volume all the time.
Oh, right.
Right. It's going to change at that rate. Yeah.
If it was
Okay.
rectangular.
The question asks, how fast is the water level rising when the water is 6 feet deep? It seems a very benign, not very hard to do problem, but it's tough, folks. So stay with me. What should we do first?
Draw a picture.
Good. Draw a picture. That's going to have to do. And we start putting things on it. Are there any things that are not changing with time? And what is the height?
10 feet.
Okay.
Radius.
The radius is not changing either. Well, not on the tank, it's not, right? Okay, so here's the radius, and it is 5 feet. Okay, and the water's filling up. And what do you want to call the depth of the water? What do you want to call this? Because it's changing, right?
Yeah.
What?
D.
No, because I'm thinking D.
I want to call it H because it will match the formula for the volume of a cone. Thank you. The radius of the water part that's been filled up, what do you want to call it? It's changing, right? As it fills up, it gets bigger. R does. So this is a changing variable. Okay. So I've got those on there. What is it that they gave us? What information did they give us?
The fill rate,
Which is, what are we going to call that, calculusly speaking?
the HDT,
No,
the RDT.
no.
The
It's the rate at which the volume is changing.
I would have got there eventually.
The volume is filling up. The volume is changing as we go along, and it's changing at,
Nine.
is it positive or negative? Are we draining or filling?
It's filling, so it's positive.
9 cubic feet per minute. That I'm not gonna use. I'm just gonna use the 9, but I'm gonna keep reminding myself. It's cubic feet that we're filling up. 9 cubic feet per minute. I'm here to tell you, this is no garden hose filling this up. Okay? So that's what the 9 is. It's the rate at which the volume is changing. You can tell because it's volume. It's got cubic feet. Okay? What is it? What else did they tell us? Did they give us an R? Did they tell us the value of this at a certain amount of time? Did they give us an H at a certain amount of time?
Yeah, when it's 6 feet deep.
When it's 6 feet deep? So
Yeah.
when H is 6? Okay. Did they give us anything else?
Look for how fast the level's rising.
Which would be what?
DHDT.
We wish to know DHDT. And I want you to know, what's the relationship between all of these things? What formula are we going to use, geometrically speaking?
Volume of the cone.
Which is?
1/3.
Oh, I got the pi. What information is conspicuously absent? R and DRDT. It's not there. Now, the author offers you 2 solutions because R is so conspicuously unknown anything about it. I'm only going to teach you one, and I suggest you grab onto it. This is the easiest one by far. Okay. The trick, if you notice that one of them, there's 3 variables in there, there's a V, an R, and an H, and there's almost nothing. Well, there's nothing known about this R right here as it changed. Nothing that was given to us anyway. So that's a clue to you to take your equation before you do anything to it, like plug anything in, do any deriving, do anything, and see if you can't replace R with something that has an H in it. And it has to do with this picture and these similar triangles. I didn't leave myself enough space to record this, so I'm going to do it way, way over here. I'm still on, yeah. Isn't it true that in all cases of cones of water, just cones of water, no matter how it's filling up, that the radius of the water part will compare to the height of the water part in a ratio of 1:2?
Yes.
It has to, because this radius and this height are in a ratio of 1:2. And any similar triangle that you draw, I don't care how full the thing is, any similar triangle that you draw is going to have a right angle here. And whatever this height is will compare to this radius 2:1. Whatever this height is, total height, will compare to that radius of water if it's that full, 2:1. So I don't know what it's going to be, but I know that R compares with H in a ratio of 1:2 if I put R on top. You follow me or not? Bailey? You following me there? Yeah, it comes down to the similar triangles. That's what makes this kind of rough.
So R is equal to 1/2
Right. 2R equals H, and so R can be replaced with H over 2. Because of the similar triangles.
The original is 10 and 5.
Because that's the ratio of the original. Yes.
Nice.
Yes.
Yeah.
Everybody seeing where we're getting that from? We're getting a static ratio. This was 5:10. We're getting a static ratio and a moving ratio, but they must maintain that ratio all the way up as we fill. If you're talking about a cone of water, its radius compared to the height of that water column is gonna be 1 to 2. You follow that?
Oh, yeah.
That's where we're getting that from. So now, before I do any deriving, I'm gonna rewrite this thing. Replacing the thing I have no information about with things that I do have information about. Replacing the R with an H over 2. That's what it's equal to in all cases of filling it up. You following me there or not?
Yeah.
That may seem really hard to you, but that's gonna make this way easier than his second method is, or his first method, or whatever he does. He does something with R and the R to T, and he still pays attention to this ratio. We gotta drag all these things around. It's horrible. Try to get this written in terms of one variable based on facts of the picture. Then what you have is pi, if you think about it, pi h cubed over 6. No, 12. Gotta square the h times that h is h cubed. Square the 2, that's 4 times that 3 is 12.
Easy peasy.
So I'm gonna pull it back apart actually. I'm gonna leave the constant out here and have an h cubed here. And that doesn't seem too bad to derive if you do a little algebraic cleanup. You okay with that?
Mm-hmm.
Now we're ready to derive. dv dt is equal to, watch this, pi fourths, right? H squared dh dt. Because the 3 over that 12 makes it 1/4.
Right.
Okay. And what do we want to know? dh dt. So I'm going to solve for that before I do any plugging in. I'm going to get dv dt divided by pi fourths h squared. I know that's a mess, but it's not very hard for your calculator. You could do some inverting and multiplying and stuff. I'm just going to plug things in. You ready? It's going to be 9 over pi h squared over 4 equals, except for what's h? 6. Equals dh dt. Because these numbers are so nice, I can continue working on that. So it's going to be 9 times, well, not times, 9 divided by 9 pi. That's how the height is changing. 1 divided by 3.14 approximately. At the moment that it is 6 feet filled. That's how fast the height is changing at that moment. Can you see that it's going to change slower and slower and slower as we fill it up?
Yeah.
Each ring of this is going to hold more and more and more water. It takes longer to fill it.
Right. Because of circumference.
It's because the way it moves.
Because of the way it is.
Did you follow all that? That can be rough. It isn't that hard, but here's the main thing. When you're done listing these things out, if there's something, whichever one you know, whichever variable you know the most of, you want to solve the other one in terms of it so that you can make a replacement before you derive. Otherwise, you're going to have too many variables and too many unknowns. You're going to have to go hunt down. Okay? Now, one more problem. And they call it the sliding ladder. I'm not going to do the sliding ladder problem for you. It's a very, very classic problem. All teachers do it. I'm not. Instead, I'm going to do another problem for you that is more like what you're going to be faced with on quizzes and tests. This one turns out quite interesting. I want you to look at, is number 29 assigned?
That's a good question.
It is. 29 is not assigned? Okay, well, this would be a good one to demonstrate for you then. Because there will be others that are related to this that will help you get a start on it. The 30s, I think it's assigned and it's pretty rough, but this will give you some idea about it, about 30. 29 is talking about some guy walking at night along a sidewalk toward a street lamp that is on, and we wish to know as he walks, how fast is his shadow changing size? So here's a scenario. We assume, and it's a good assumption, that street lamps are perpendicular to the ground they are in. So we're going to assume a flat ground. Here's the street lamp up here, and here it looks, I don't know, something like that. And there's a light in here, it's a light bulb. Here's the guy. I'm not gonna draw a guy, I'm just gonna draw how tall he is. There's the guy, and he is walking this direction. And his shadow behind him, and it will be a shadow behind him. If the only shadow is cast by this lamp, the shadow will be behind him, right?
Yep.
Okay. All right. So listen to the details. It says, a man 6 feet tall. Is that a static value? How tall is the lamp?
16.
16, and this guy's 6?
Yep.
I'm gonna make him just a bit taller then, maybe about a third. That's a little bit tall. Okay. Anyway, so this guy is 6 feet tall, and that's not gonna change, so I'm gonna put that right on my picture. The street lamp is 16 feet tall up to the bulb that's casting the shadow. Those are static values. I can put them on the picture. It says, and the man walks at a rate of 5 feet per second. That means we need some variable names. This is changing, right? As the man walks that way. What do you want to call it? Good. Okay. What have they told us with that 5 feet per second?
-5.
They've given us the XDT. And it's equal to what?
-5.
It's equal to what? -5. Because that variable is diminishing as time moves along. Keep track of that, folks. So the XDT is -5. And then it says, at what rate is the length of his shadow changing when he is 10 feet from the base of the light? What have they just told us with the 10? X. They told us this length at a particular time that we want to freeze the picture. And what do we want to find? We haven't given his shadow. I extend my flat sidewalk out a little ways. How do I figure out geometrically anyway, just how long his shadow is at this instant of drawing?
Line from up the street light, like touching his head.
Yeah.
I don't know how to.
Touching his head is exactly right. He's up here, he's drawing pictures for me in the air and they're perfect. He goes, this is how you determine his shadow length. So I'm not gonna go from the bulb, I'm gonna go from the base of this and pretend that's where the bulb is. And you have to draw a line that hits that guy right on the top of the head because this is his shadow, if you know how shadows work, right? Now, what do you want to call this? I don't want to call it S because my S's look like 5s.
How about Y?
How about X?
W.
W?
W sounds pretty good.
Okay, all right, we'll call this W. So we now have the length of his shadow there, and we've got some, both of those are changing. The X and the W are changing. What, now that we've got something on the shadow, what is it they want us to find? dWdt. Okay, have they given us, read through it again one more time and see if there's any information I don't have that I haven't put on the picture in some way or another or listed. Got everything? Okay, so when we have everything and we've listed it or put it on the picture if it's static, variable if it's not, now we've got to find out how all this stuff is related. What math ties them together? Here's an assumption. Here's an assumption. People don't generally walk slanted. We're saying, assuming he's perpendicular. Does that help at all? What have we got that ties all these things together?
Similar triangles?
Similar triangles, exactly. And similar triangles have proportional sides. So what would you like to put as some sort of an equation?
W over X equals 6.
X over X.
You want me to do the variables first? What'd you say?
W over X.
W over X?
W over 6.
W over 6, not X over 16. X.
W over,
6.
okay, I'll do that. As,
X plus W over 16.
oh my God.
That makes it a lot.
Oh, yeah, that's.
This long leg is to this height as this long leg is to its height. See it? Everybody clear? I'm gonna cross multiply again to flatten things out before I try to do any differentiating. And I'm gonna I was gonna say I was gonna reduce these, but you guys did put those together in a ratio. I'll leave it where it is. 16W equals 6X plus 6W. Right?
Yeah.
Oh, well, I can even do a little bit more to this before I start deriving. And I can even do a little bit more if I wanted to keep things small. Is that okay? So I cleaned up this is the geometric relationship, similar triangles. I did the algebra, I cleaned it up as much as I could. Now I want to derive, what's this derivative? And what do we want to know? dw dt? Plug it in. dw dt is equal to 3 times negative 5 over 5, which is
-3.
negative 3 what?
Feet.
That's how his shadow is changing. His shadow is getting shorter by 3 feet every second that he walks. What's weird about this one is, think about this with me for just a minute, because I want to talk to you about it. What's weird is this never came into it. We never put that 10 in anywhere. How come? Because the thing we derived was linear. And the derivative, or the slope of any line is a constant. It doesn't matter whether he's 10 feet from the light or 100 feet from the light. It's still casting enough light to cast. Or 2 feet from the light. It makes no difference how far he is, because as long as he's continuing to walk at a steady rate, the relationship is linear, so the derivative is constant. This rate of change will happen no matter how far he is from the light. That's how fast his shadow will be changing if he keeps walking at the same rate. Okay? So that was interesting. We got a 10 here, but it was worthless to us because what we derived was linear. And the slopes just came out. They don't differ. The slopes are the same all the way through. Okay. That's all I have for you. I can demonstrate all day and I'll demonstrate all the exercises you got. You're going to start thinking for yourselves as far as this goes. Drawing your own pictures, drawing your own relationships, doing your own algebra. Make sure, people, that you do not put values on here that are not static. And make sure that things that are diminishing, you assign their rate of change to be negative. There you go.
Do you know what's happening?